On one specific night in August 2024, the James Webb Space Telescope recorded a single, faint point of mid-infrared light sitting beside the closest sun-like star to our own solar system. The signal was real, statistically significant, more than 10,000 times fainter than the star itself, and positioned at almost exactly the kind of distance where a planet capable of hosting liquid water might plausibly orbit. Astronomers had been searching for exactly this kind of signal around exactly this star system for decades. And then, when Webb looked again 7 months later, and then again 2 months after that, the object was simply gone. Not fainter, not shifted slightly out of position, completely absent from the data, as if it had never been there at all. This is the real story of what James Webb actually found near Alpha Centauri A, why the apparent planet vanished not once, but twice after its first detection, and how a team of astronomers used millions of simulated orbits to figure out exactly how a real physical world could disappear and reappear from view without ever actually going anywhere. I'm your host, and this is your channel. If you want the real science behind the biggest discoveries in space, subscribe now, because we're just getting started. To understand why this specific star system generated this level of sustained, patient scientific attention, you first have to understand exactly what makes Alpha Centauri so genuinely significant in the broader search for planets beyond our own solar system. Located just over 4 light-years from Earth, Alpha Centauri isn't a single star at all, but a triple star system made up of Alpha Centauri A and Alpha Centauri B, 2 sun-like stars locked in a binary orbit around each other along with Proxima Centauri, a much fainter, more distant red dwarf star that orbits the central pair from considerably farther out. Alpha Centauri A specifically is remarkably similar to our own sun in mass, temperature, and general characteristics, making it, in the language astronomers sometimes use, a genuine solar twin. In its sheer proximity, the closest star system to our own entire solar system, has made it one of the single most compelling, most persistently studied targets in the entire search for planets beyond our own solar neighborhood for decades. That proximity cuts both ways, though, and understanding why makes clear exactly how difficult finding a planet here has actually been. Being close to Earth makes Alpha Centauri appear unusually bright in our sky, which sounds like it should make detection easier, but for direct imaging specifically, the technique of actually photographing a planet's own light rather than inferring its presence indirectly, brightness is the enemy, not the ally. A star's overwhelming glare drowns out the comparatively faint light of any orbiting planet, and the closer and brighter that star appears, the more severe that glare problem becomes. Compounding the difficulty, Alpha Centauri A doesn't orbit alone. Its binary companion, Alpha Centauri B, sits close enough in the sky that its own light frequently contaminates observations aimed at the primary star, adding a second independent source of overwhelming brightness that any planet-hunting instrument has to somehow account for and subtract out. The search for planets around this specific system goes back further than most people realize, and it's worth tracing that history because it shows just how much patient, incremental effort led up to Webb's eventual involvement. Kevin Wagner, an assistant research professor at the University of Arizona's Steward Observatory, led an earlier search back in 2019, using the European Southern Observatory's Very Large Telescope in Chile, and identified a tentative, faint signal, subsequently designated C1, hinting at the possible presence of a planet. That early result, published in 2021, wasn't confirmed with enough confidence to be treated as a firm detection, but it was suggestive enough to keep the target on astronomers' radar, waiting for a more capable instrument to eventually take a closer, more decisive look. That more capable instrument arrived in the form of James Webb's Mid-Infrared Instrument, commonly abbreviated MIRI, equipped with a coronagraph, a specialized component specifically designed to physically block out the overwhelming light of a target star, allowing much fainter objects sitting nearby to potentially be detected. In August 2024, a research team pointed Webb's coronagraphic mask directly at Alpha Centauri A, specifically engineering the observation to suppress the star's own blinding light as thoroughly as possible. Even with that suppression in place, the nearby light from companion star Alpha Centauri B still complicated the resulting image considerably, requiring the team to carefully mathematically subtract out contaminating light from both stars before they could examine what remained. Once that subtraction was complete, a real distinct signal emerged in the data, a point source of light more than 10,000 times fainter than Alpha Centauri A itself, sitting at an angular separation of about 1.5 arc-seconds from the star, corresponding to a projected physical distance of roughly twice the distance separating Earth from our own sun. The team, being appropriately careful, scientists working with a genuinely exciting but still preliminary result, didn't rush to declare victory. They systematically tested and ruled out the most obvious alternative explanations for what the signal could represent. Could it have been a passing asteroid? coincidentally crossing through the field of view at exactly the wrong moment? The team determined this was unlikely, given the object's specific characteristics and position. Could it have been a distant, unrelated background galaxy happening to sit in almost exactly the right spot in the sky purely by chance? Again, ruled out as statistically improbable based on careful analysis. Could it have simply been a detector artifact, some kind of instrumental glitch or processing error, rather than a genuine astrophysical signal at all? The team tested for this too and found nothing, suggesting the signal was anything other than real. Aniket Sanghi, one of the researchers involved in the analysis, later summarized the team's overall confidence in the initial detection directly, describing the observation as genuinely exciting, while also being clear that the team recognized they needed considerably more data before reaching any kind of firm, confident conclusion. That need for more data led directly to the part of this story that turned a promising detection into a genuine, months-long scientific mystery. The research team scheduled additional follow-up observations of the same target using what's called director's discretionary time, a mechanism that allows astronomers to request additional Webb observing time outside the normal competitive proposal process, specifically to pursue a result urgent or significant enough to warrant expedited follow-up. Those additional observations took place in February 2025 and again in April 2025. And in both of those follow-up sessions, conducted using the same instrument, the same basic observational approach, and the same careful analysis techniques that had successfully detected the object back in August 2024, the team found absolutely nothing resembling the point source they'd previously identified. The object, whatever it actually was, had simply vanished from the data entirely, not once, but across two entirely separate observation windows. This is genuinely where the story could have ended in ambiguous disappointment, with a promising but ultimately unconfirmed signal quietly filed away as an interesting but inconclusive result. Instead, the research team treated the disappearance itself as a scientific puzzle worth actively solving, rather than simply accepting it as evidence the original detection had been some kind of fluke. If the August 2024 signal really had represented a genuine physical planet, then a real planet doesn't actually vanish. It moves continuously along its orbit, and depending on exactly where that orbit carries it relative to its host star and Webb's own specific viewing geometry at any given moment, it's entirely possible for a real physical planet to become effectively undetectable during certain phases of its orbit, not because it isn't there, but because its position relative to the star, combined with the practical limits of the coronagraph's ability to distinguish extremely close-in objects from the star's own residual glare, could plausibly hide it from view during specific observing windows without ever requiring the object to have disappeared at all. To test this hypothesis rigorously, rather than simply speculating about it, the team turned to computer modeling, running an enormous number of simulated orbits, millions of individual possibilities, each representing a different combination of orbital shape, size, and orientation that a real planet around Alpha Centauri A could plausibly follow, then checking which of those millions of simulated scenarios would actually be consistent with a planet being clearly visible during the August 2024 observation, while simultaneously being effectively invisible to Webb's specific instrument and viewing geometry during both the February 2025 and April 2025 follow-up windows. Sanghi described the key finding that emerged from this massive simulation effort directly. The team found that in fully half of the possible orbits they simulated, the planet would have moved too close to its host star during the February and April 2025 observation windows to have been visible to Webb at all during either of those specific attempts. In other words, an object following a real, physically plausible orbit could very easily explain exactly the pattern of detection and non-detection the team had actually observed without requiring any exotic explanation, and without meaning the original August 2024 signal had been some kind of error or artifact. Based on the combined analysis, incorporating the object's measured brightness during that initial detection along with the constraints imposed by the extensive orbital modeling, the research team's best current interpretation is that they've likely found a gas giant planet, roughly the mass of Saturn, orbiting Alpha Centauri A along a genuinely eccentric, elongated elliptical path that carries it between roughly 1 and 2 times the distance separating Earth from our own Sun at different points in its orbit, a variation substantial enough to plausibly explain why the planet was clearly visible at one specific point in that orbit and effectively hidden at others. The candidate object has been formally designated S1 in the team's published analysis. It's worth pausing to appreciate exactly why a planet like this, if ultimately confirmed, would represent such a genuinely significant achievement in the broader field of exoplanet science, because its specific characteristics set it apart from almost every other planet ever successfully directly imaged. Sanghi laid out the significance plainly. If confirmed, he explained, the potential planet seen in Webb's image of Alpha Centauri A would mark a genuine new milestone for exoplanet imaging efforts specifically. Of all the directly imaged planets discovered to date, he noted, this one would be the closest to its own host star ever successfully imaged this way. It would also be the most similar, in both temperature and estimated age, to the actual giant planets in our own solar system. And, given Alpha Centauri's extreme proximity to Earth, it would be the nearest directly imaged planet to our own homeworld as well. That distinction, being both close to its star and similar in temperature to our own solar system's giants, matters enormously within the specific technical context of direct imaging as a detection method. The overwhelming majority of exoplanets successfully imaged directly up to this point have been young, still hot giant planets, sitting relatively far from their host stars, precisely because that combination of youth, residual formation heat, and wide physical separation makes them easier to distinguish from their star's overwhelming glare using current instrument technology. A planet like S1, if it's confirmed as real, would represent something genuinely different. A more mature, cooler giant planet, positioned considerably closer to its host star than the typical directly imaged exoplanet population. Precisely the kind of world that has historically been far more difficult to detect, using direct imaging techniques at all. Successfully confirming an object like this would demonstrate that Webb's coronagraphic capabilities are genuinely capable of pushing into this more challenging, more scientifically valuable category of target, potentially opening the door to detecting similar, mature, closer-in giant planets around other nearby stars in the years ahead. There's also a secondary puzzle embedded in the data that researchers have continued working through, involving the planet's measured brightness. According to the team's analysis, the candidate planet appeared somewhat brighter in Webb's observations than a simple, straightforward model of a Saturn-mass gas giant would typically predict, and researchers have proposed several plausible explanations for that specific discrepancy, none of them mutually exclusive, and none requiring anything beyond conventional planetary physics. One possibility involves zodiacal dust, fine interplanetary dust particles that could be contributing additional infrared brightness to the overall signal, adding a layer of thermal emission on top of whatever the planet itself is producing. A second possibility involves the planet's rotation and orientation, since a rapidly rotating planet, if observed from a particular angle relative to its poles, could present more of its warm, glowing surface area to Webb's instruments than a more conventional viewing geometry would allow, artificially boosting its apparent brightness without requiring the planet itself to be unusually hot. A third possibility, genuinely evocative given our own solar system's most famous ringed planet, involves the candidate having a system of rings similar to Saturn's own, which could meaningfully increase the total reflective and thermally emitting surface area contributing to the object's overall measured brightness. None of these explanations has been confirmed over the others, and researchers have been explicit that distinguishing between them will require additional observation and analysis. It's worth being scrupulously honest about exactly where this discovery currently stands, because that honesty is precisely what separates credible, careful science from an exaggerated headline. NASA's own official language describing this finding in its August 2025 public release uses careful, deliberately qualified terminology throughout, describing strong evidence for a giant planet, language that reflects genuine scientific confidence in the underlying signal while stopping meaningfully short of declaring a formally confirmed discovery. The core limitation remains exactly what it was from the beginning. Additional observations are required before this candidate planet can be treated as a confirmed cataloged world, rather than a strong, well-supported, but still provisional candidate. That's not a hedge added for legal caution. It's an accurate, honest reflection of where the actual science genuinely stands as of this recording. There's also a specific point worth clarifying directly, because casual coverage of this story has sometimes blurred an important distinction. Some reporting on this candidate planet has referenced its position within Alpha Centauri A's habitable zone, the specific range of orbital distances where a suitably constructed rocky planet could theoretically maintain liquid water on its surface. That description is accurate as far as it goes. The planet's estimated orbital distance does fall within that general zone, but it's essential to be clear about what that specific fact does and does not actually mean. S1, if confirmed, is a gas giant comparable in mass to Saturn, with no solid surface of any kind, and almost certainly no realistic possibility of hosting life as we understand it, regardless of its specific orbital distance from its star. Being positioned within a habitable zone is a statement about distance and available stellar energy, not a statement about a specific planet's actual habitability, which depends enormously on that planet's fundamental physical nature, atmosphere, and composition. NASA's own Broader public materials on the concept of habitable zones are direct about this exact point, stressing that orbital distance alone never establishes whether a given world is actually habitable. Kevin Wagner, whose original 2019 search first put this specific target on the map years before Webb's own involvement, offered a genuinely enthusiastic assessment of where this entire multi-year effort has now arrived, one worth taking seriously given his direct personal familiarity with just how difficult this particular search has been. This discovery, he said, is shaping up to be one of the most exciting results in astronomy of the entire decade. That's a significant statement from a researcher who has spent years working on exactly this specific problem, watching an initial, tentative 2019 signal slowly develop, through Webb's far more capable chronographic instruments, into a genuinely compelling, if still not fully confirmed candidate discovery. So what happens next, and how will astronomers actually settle this question with real confidence, one way or the other? The research team's own stated path forward involves continued observation of the Alpha Centauri system using Webb, specifically timed and planned around the refined orbital predictions generated by their extensive computer modeling, attempting to catch the candidate planet during a portion of its orbit where the models suggest it should once again become visible to the telescope's instruments. If those carefully targeted follow-up observations successfully detect the object again in a position and brightness consistent with the orbital predictions the team has already developed, that would represent genuinely strong, mutually reinforcing confirmation, moving this candidate significantly closer to formal, confident acceptance as an actual confirmed exoplanet. If, on the other hand, continued targeted observations consistently fail to detect anything, even during windows the orbital models predict the object should be visible, that would understandably raise renewed questions about the original interpretation, requiring researchers to seriously reconsider whether the August 2024 signal represented something other than a genuine orbiting planet after all. It's worth placing this specific effort within the broader context of what Webb has already accomplished in the field of direct exoplanet imaging, because the Alpha Centauri A candidate represents part of a larger, ongoing pattern of genuine progress. Webb captured its first ever direct image of an exoplanet, a gas giant called HIP 65426b, back in September 2022, within its very first year of full operation, an early, important proof that the telescope's coronagraphic instruments genuinely worked as designed. In June 2025, a separate research team successfully confirmed TWA-7b, a planet roughly the mass of Saturn orbiting a much younger star, representing the lightest planet ever successfully detected through direct imaging. Up to that point, another genuine milestone for the technique. And in July 2026, an entirely different research approach led to the discovery of Beta Pictoris d, a planet found not through conventional direct imaging at all, but through a related but distinct technique involving moderate resolution spectroscopy, detecting the specific chemical fingerprint of a planet's atmosphere directly within a star system's overall spectrum rather than isolating it as a distinct point of light in an image. Taken together, these results demonstrate a genuinely active, rapidly maturing field, with astronomers steadily pushing the boundaries of what kinds of planets, at what distances, masses, and temperatures can actually be detected and confirmed using Webb's specific combination of instruments and techniques. The Alpha Centauri. A candidate occupies a genuinely unique, valuable position within that broader body of work, precisely because of its combination of extreme proximity to Earth and its host star's close similarity to our own Sun. Even setting aside the specific, still unresolved question of S1's ultimate confirmation, the broader Alpha Centauri system remains one of the single most scientifically important targets in the entire search for planets beyond our own solar system, precisely because its extreme closeness to Earth means that any planets eventually confirmed there, whether ultimately habitable themselves or not, would represent by far the most accessible, most thoroughly studiable planetary system beyond our own that humanity is ever likely to examine in genuine detail, using both current and future generations of increasingly capable telescopes. So here is where this genuinely, honestly stands, based entirely on NASA's own published statements, the peer-reviewed analysis behind it, and the direct, on-the-record comments of the researchers who conducted this work. In August 2024, James Webb detected a real, statistically significant point source of light near Alpha Centauri A, the closest sun-like star to our own solar system, consistent with a Saturn-mass gas giant planet. That same signal then failed to appear in two subsequent observation windows in February and April 2025, a genuine puzzle that the research team resolved not by abandoning the original detection, but through careful orbital modeling, demonstrating that a real planet, following a genuinely plausible elliptical orbit, could easily produce exactly this pattern of visibility and apparent disappearance without ever requiring the object to have actually vanished at all. The resulting candidate, designated S1, remains formally unconfirmed, exactly as NASA's own careful, qualified language describes it. But if it does hold up under continued observation, it would represent the closest directly imaged planet to its own host star ever found, and the nearest directly imaged planet to Earth in the entire history of the technique. That is not manufactured drama built around an exaggerated headline. That is the honest, careful, genuinely exciting state of one of the most scientifically valuable ongoing investigations in modern exoplanet astronomy, still very much unfolding in real time. If this kind of story is what you come here for, one grounded in exactly what NASA's own researchers actually measured, modeled, and directly said, rather than exaggeration, hit subscribe and turn on notifications, because there's clearly more waiting to be confirmed in our own closest stellar neighborhood. Drop a comment telling me whether you think S1 will ultimately be confirmed as a real planet, and share this with someone who still thinks Alpha Centauri is just an empty patch of nearby sky with nothing left to discover.